Let's have a look at oxidation numbers. This is a concept that applies to pure elements such as oxygen, sulfur, iron, or any element at all. And it also applies to compounds such as diphosphorus pentoxide and potassium dichromate. Even ions are susceptible to analysis by oxidation numbers. But in this lesson, let's just look at compounds and compounds only. I want you to consider this one here, this substance, chromium fluoride. We need to be able to name it by knowing what chromium's charge is. Well, we analyze it by looking at the fluorine and saying it's -1, and we come up with chromium 3 fluoride. We can do it with lead oxide. Oxygen is -2, so we can calculate that the lead must be +4, and we get lead 4 oxide. Even in sodium and selenide, now I've chosen selenide because it's unfamiliar, but you still know that sodium is +1, meaning selenide must be -2. We do these calculations all the time, where fluorine is -1, oxygen is -2, hydrogen and the alkali metals are +1. So let's look at this one, which is a bit of an odd-looking compound because it has two metals, sodium and chromium. Now what's going on is that chromium is associated with oxygen in a covalent bond, which is unusual. Chromium metals have covalent bonds, but they do. Well, let's analyze it in the same way, letting sodium be +1 and oxygen -2. It's a compound, so it all has to add up to 0. And if you look at it, you've got a couple of 1s, you've got the chromium, and 4 -2s. So if we do a little bit of algebra, we can work out that chromium is +6. Well, this is the oxidation number of chromium, and it has some interesting uses. I want to say that it's not the charge of chromium. Chromium +6 doesn't exist. But first, let's look at another compound, diphosphorus pentoxide. Letting oxygen be -2, we can quickly calculate that for this to add up to 0, the phosphorus has an oxidation number of +5. Here's 3 compounds. Consider pausing the video and calculate the oxidation number of each of these elements, nitrogen, chromium, and xenon. Well, I've started with the nitric acid here, HNO3. Hydrogen is +1, oxygen -2. You can quickly see that the nitrogen is +5. That's its oxidation number. Well, what about chromium here? There's a couple of them, and they have to add in with the 2 potassiums to balance off that -14. Chromium is +6. And xenon, here with 6 fluorines, is also present with an oxidation number of 6. So let me give an example with carbon of how oxidation numbers can be useful. I'd like to look at carbon dioxide, at sugar, sucrose in particular, and methane. Well, if we calculate oxidation numbers, here the carbon must be +4 in carbon dioxide. In the sugar, the hydrogens are +1, and there's twice as many as oxygen. Carbon has to be 0. And in methane, carbon is -4. Let's make a little vertical number line here with methane at the bottom, sugar in the middle, and carbon dioxide at the top. Now, the oxidation number lets us know about whether we can burn them or not. For example, consider carbon monoxide. Because it's not gone all the way up to +4, because it's +2, we can burn it. You cannot burn carbon dioxide, but you can burn methane. Well, that's about it. Thanks.